A physics project that I did with the grandkids was building a metal detector and learning how it works. But before we could do that, first we need to learn some important principles in the field of acoustics. The kids already understood that production and perception of sound has to do with vibration. They've experimented with homemade musical instruments, and when they built homemade speakers, they learned how to convert electrical vibration into magnetic vibration, into mechanical vibration, into sound. For our first lesson in this series, we need 2 tunable audio tone generators. The Internet comes to the rescue with this wonderful website, onlinetonegenerator.com. When you open the website, this is the first thing you see. Scroll down a bit and you find it is ready to play a tone. Just click the play button and you hear the note it generates. If you have a piano nearby or other suitable musical instrument, try to find the note that matches that tone. Or you can use the online piano keyboard provided for us by clicking on the piano keyboard below the tone generator menu on the left side of the screen. Let's check this out, starting with middle C. That's not it. We need to go higher. That's it. The note is A above middle C. Now we click the browser tab to go back to the tone generator and turn it off for a moment. Let's make this exercise a little easier by opening the tone generator and piano keyboard in separate browser windows and arrange them so that we can look at both of them at the same time. Let's repeat the test that we just did. Now click your mouse in the box that says 440 Hz, delete that number and double it. Type 880. Then hit the Enter key or click the play button and find that note on the keyboard. It's A above high C. So just by doubling the frequency, we move up exactly 1 octave. Double the frequency again. 880 times 2 is 1,760. Click play. And that also is A, 1 octave higher. Let's go back to 440 Hz and cut it in half. That's 220 Hz. That note is A below middle C. Let's maximize the piano web page. Scroll up and click on the menu and find a link to a list of piano key frequencies. Here in the right-hand column, we find the frequencies of all the notes on a piano keyboard. Scroll down a bit and we find our A above middle C, 440 Hz. Perhaps we need to explain what the word hertz means. It has nothing to do with a car rental company. In my early ham radio days, we referred to audio and radio frequencies in cycles per second. Nowadays, engineers refer to cycles per second as hertz, in honor of the German physicist Heinrich Rudolf Hertz, who is credited as the first person to prove the existence of electromagnetic radiation, or radio waves, as we often like to say. I'm a bit old school and still favor referring to frequencies in cycles per second. So let's look at what we just did on an oscilloscope. Here's what 220 Hz looks like. Double it to 440 Hz. Double it again to 880 Hertz, and double it again to 1760 Hertz. One of the fun things to do next is to find out what is the frequency range of our hearing. How high can the frequency go before you stop hearing a tone? When we tried it, the grandkids heard much higher frequencies than I'm now able to hear. The limit of the lower frequency has more to do with the size of the speaker, since small computer speakers have difficulty producing bass tones. Now let's change gears a bit and run two different tones at the same time and hear how they interact. If you want to do this as a demonstration for a class, this works best and is more fun using two computers, each one running the tone generator app. The website lets us do the same thing on this page, as it allows us to run multiple tones simultaneously. But here we'll run the tone generator in two separate browser windows. Both tones are set to the default frequency, 440 cycles per second. First, click the one on the left, then the one on the right, and then both together. Okay, nothing surprising there. Now let's increase the frequency of the one on the right just 1 cycle per second. So now it's 441 Hertz. And let's play that. Now let's stop the 441 Hertz tone and play 440 Hertz. If you can hear the difference, you have better tone discrimination than I do. To me, they both sound the same. But let's hear what happens when we play them together. Interesting. Let's see this on the oscilloscope. Here's 440 Hertz. Then 441. And then both together. We can both hear and see the slow pulsing when we play them together. When we play each tone separately by itself, the volume is steady. But when we play them together, we hear only one tone, but it's pulsing. What causes that? Because the two frequencies are not exactly the same, part of the time the two waveforms are in sync, and they increase the volume of what we hear. And part of the time the two waveforms are 180 degrees out of phase, and they cancel each other out, momentarily making the tone go quiet. We can precisely calculate the rate at which these waves go in and out of phase. Let's run this test with the timer and count the speed of the pulses. The frequency difference between these two tones is exactly 1 cycle per second, and the frequency of the pulsing that we hear is 1 pulse per second. That's no coincidence. Now let's increase the frequency on the right to 442 Hertz. The difference here is 2 cycles per second. Let's hear what that sounds like. We are hearing 2 pulses per second. So let's increase the frequency one more to 443. And we hear 3 pulses per second. And one more. And then one more. This pulsing you hear is what engineers call the beat frequency. Now let's play these two tones separately and see if we can hear the difference. First, the 440 Hertz on the left. then 445 on the right. Okay, I can hear that difference. With 2 or more computers, the kids can make a game of this. One student on his computer will set the tone generator at a random frequency and play the note. Then another student on another computer tries to identify that frequency by exactly matching the tone. We can demonstrate that here on this screen. I set the tone on the left to some arbitrary frequency, and let's use the tone generator on the right to see if we can figure out what that mystery frequency is. 440 is too low. About 500 hertz. 600. 700. 800. Wow, listen to that. We're pretty close. Do we need to go higher or lower? Well, let's increase it by 10 cycles per second. 810. Whoops, that's the wrong direction. We need to go lower. Let's go back to 800 and drop it by 10. 790. Wow, we're really close now. We're only off by 1 cycle per second. What does 791 sound like? No, that's not it. We need to go the other way. 789. A perfect match. Let's see. Okay, that's what beat frequency sounds like when 2 tones are close in frequency to each other. But is there a beat frequency when 2 tones are so far apart that we can't hear any pulsing between them? The answer is yes, and we will explore that in the next video. Connecting to the output will be simple enough, because here's your output.
Just snap that there.
Snap that right there, right?
Now we're going to do the negative.
So that one we have to connect over to